Hello everyone, my name is Zihan Wang. Thank you for coming to this video. I'm going to present our work, Reconstructing Training Data from Model Gradient, Provably. This is the joint work with Professor Jason Lee from Princeton University and Professor Qi Lei from New York University. I'd like to especially thank to Professor Qi Lei because I adopted some of her slides for this talk. Our work is based on the setting of federated learning. Federated learning is a learning technique that the training is done by multiple individual local devices and their own private datasets. The working process is shown in the figure. That first, local devices download the current model from the cluster and compute and update based on local data. Then, devices send the model update to the cluster, and the cluster aggregates the updates and improves global model. This process goes round and round. Federated learning are considered safe, since local training data can only be accessed by its device, and only gradient information is reported to the cluster. However, the gradient is quite informative that the leakage of private data may happen. In fact, federated learning is vulnerable to privacy attacks. We first introduce some formal notations. We have a local batch of data S with labels from x1y1 to xbyb with batch size b. The prediction model is a neural network and is parameterized as f theta. The loss function L is quadratic in following settings, and the local update G is based on local data x1 to xb. In federated learning, the structure of network, parameter theta, and gradient G are known by the cluster. The cluster can even set proper parameter theta specifically to help attacking private data. The goal of privacy attack is to recover the unknown dataset S from G. Most of the previous work on attacking the private data in federated learning is to matching the true model gradient with the gradient generated by dummy data. Formally, they try to find data x and y, minimizing some distance d between real and dummy gradients. This method needs to solve a very complicated non-convex optimization problem. Most algorithms first randomly initialized a dummy data x hat and y hat, and then updated them through iterations. Therefore, it needs to query the model for multiple times to compute dummy gradient in each iteration. Besides, prior knowledge are used in most of these works, and moderated trained models are considered to be the best setting since random network has no memorization of the training process, which is considered important to recover data in previous work. Our work, however, is to answer the following fundamental questions that may challenge some consensus in previous work. First, can we only query the model once to identify the training samples instead of multiple times? Second, do we need prior information for the training data, and do we need the memorization of training? In other words, is the single gradient at random initialization itself sufficient to recover training data? Finally, if the answers are yes for the questions above, can we find an efficient algorithm? To answer the questions above, we first look at a warm-up setting, two-layer neural networks. The model parameter here is composed with A and W, representing the weight of two layers respectively. Here, M is the number of hidden nodes of the network and D is the input dimension. Since the cluster can set the weight arbitrarily, we can let Aj equals to 1 over M and Wj follows standard Gaussian distribution with dimension D. The main theoretical basis of our method is Stein's lemma. It says that for any differentiable function g, the expectation of GW HBW equals to expectation of the pth order derivative of G, where W is standard Gaussian and HP is the pth Hermite function. Here we mainly consider the functions when P equals to 2 or 3. Now let GW in Stein's lemma be the model gradient over A. Then, since the gradient is known, we can compute the average of GWJ HPWJ over J from 1 to m, and denote it by Tp hat. It is approximate to its expectation according to some concentration, since W's are Gaussian. By Stein's lemma, it is equal to a weighted sum of xi's tensor power Tp. Thus, we can estimate Tp with model gradient and conduct tensor decomposition. By Kuleshov et al. 2015, the training samples x1 to xb can be identified when they are linearly independent and p is greater than or equal to 3. This method only queried once at random initialization and used no prior information, which satisfies our requirement. The only uncertainty in the method is its strategy of tensor decomposition. With different tensor methods, we may have different reconstruction error. Apart from directly conducting tensor decomposition, some other tensor methods may help improving the dimension dependency. Here we adopt the strategy from Zhong et al. 2017. We first estimate the span of training samples S by decomposing the second-order tensor T2 with VV transpose, where V is a D times B matrix. Then, we estimate the tensor T3 VVV, which is the tensor product of T3 and V's from 3 different directions. After that, we conduct tensor decomposition to get U1 to UB, just similar to the original tensor decomposition. Finally, we project UIs to the original space by VUJ equals to XJ hat and get recovered training data. Under this method, we can theoretically bound the reconstruction error. First, we need to make some assumptions on data and activation functions. For data, we need x1 to xb be linearly independent. And for activation function sigma, we require that it is ellipsis and the expectation of its third order or fourth order derivative under standard Gaussian is not 0. Note that most activation functions apply to this assumption, including sigmoid, hyperbolic tangent, ReLU, and leaky ReLU. But this is not for linear and quadratic functions. Under these assumptions, we show that the reconstruction error is order square root over D, where some log factors are omitted. In this sense, the width M scales linearly with input dimension D. Now we turn to deep neural networks with L layers. If the last 2 layers are fully connected, we can recover the features from the L-2 layer, same as the 2-layer case. Then, if the first L-2 layers are bijective, one can recover the input training samples by inverting the first L-2 layers. Specifically, reconstruction can success on fully connected deep neural networks with activation functions as sigmoid, fan, ReLU, and or leaky ReLU by setting proper weights. For ReLU, a piecewise linear function, we can set weights to be identity matrices or minus identity matrices to get the positive and negative parts of input x. As we showed in the figure, it preserves x plus and x minus in the middle layers by setting all weights to be identity, since x plus and x minus are non-negative. Then, we will get the exact input x at the last hidden layer by x plus subtracts x minus. Then it reduces to the 2-layer case. For injective activation functions, like sigmoid and hyperbolic tangent, we can simply set all weights to be identity matrices. Then we can invert the feature of the L-2th layer to identify the training labels. In deep neural network setting, we convert the problem into two-layer net cases. This implies that the depth of the network has no effect to the reconstruction error. Now we turn to the experiment part. Before showing our experiment results, we first introduce an alternative method to recover training samples that we used in experiments. Instead of using the gradient over AJs, here we can also identify training data by using W gradient. Specifically, we denote the gradient over W by G and estimate TP plus 1 hat, the average of GWJ HPWJ. Similar to the method using A gradient, by concentration and Stain's lemma, TP plus 1 hat is approximate to TP plus 1. Then we again conduct tensor methods to recover training samples. This alternative method has same order of theoretical error bound as the original one, but it performs better in experiments. Now we turn to experiment results. We first show the result of experiments on synthetic data, where the training samples are one-hot vectors and the problem is binary classification. We fix the number of hidden nodes to be m and set batch size b equals to 2, only varying the input dimension d. The left figure shows the comparison between using A gradient or W gradient when activation function is x squared plus x cubed, where the method of W gradient has smaller reconstruction error. Then we use W gradient in all further experiments since it performs better. The right figure shows the error of using sigmoid and then as activation functions respectively. The reconstruction error increases when D increases, but still quite small contrast to the high dimension D of input data. We also did some experiments on binary classification of MNIST images. In this experiment, we considered two-layer neural network and set the activation functions to be x squared plus x cubed, which satisfies the assumption of our method. For MNIST, the input dimension is fixed as 28 squared equals to 784, and the batch size b equals to 2. We compare the recovered images with original ones when varying the number of hidden nodes. The results show that the recovered data can be identified as handwriting numbers. This indicates that our method is able to reconstruct MNIST images from model gradient. Note that the reconstruction successes no matter the training samples have same or different labels. In conclusion, our method theoretically and empirically shows that, first, one single query is sufficient to recover training data. Moreover, recovering training samples does not rely on memorization or prior information. It can be solely dependent on gradient. Besides, there are some more discoveries. First, about the size of the network. We show that the width scales linearly with the input dimension d, while the depth has no effect to reconstruction. It neither helps nor hurts. Then, for identifiability, most of the activation functions is applicable to our methods. Moreover, adding gradient noise cannot prevent data leakage, since our methods do not require exact gradient. Thank you so much, and this is the end of the talk.